Welcome to our lecture on logistic regression. So sometimes we need to predict an outcome that's binary. It's either true or false, yes or no, 1 or 0. And here's a simple example that's based on a game that I sometimes like to play in class with my students called Two Truths and a Lie. So the way we play this game is we break up into groups, usually of 3 students, and then each of us has to take turns listing 3 statements, 2 of which are true and 1 of which is a lie. The other people in the group then have to try to decide which statement is true. So once they've determined, all right, we think that this is the statement that is true, then we can ask them, how sure are you? And by voting, those other people in the group have to come up with a number between 0 and 10 to represent their certainty, where 0 means totally uncertain and 10 means completely certain. So when we're all done, for each of the people in the group, we know whether the others guessed correctly, which statement is really true, and we also know how certain they were about their guess. So if we wanted to model this for the regression model, the outcome is binary, and then we have a predictor x. And just to be clear, the unit of observation in this case is every single person in the class, and the x, which is the certainty variable that is associated with the outcome y, which says if the guess is correct or false, is computed from the certainty level of the other people in that student's group. So it's a fun little example, and you'll have a chance to play around with the data set for that example later in this lecture in one of the exercises. Now, you might say, fine, yes, the outcome is binary, but we could just still use linear regression, right? We can still enter the data into the computer and run the command for linear regression. We'll get an answer. That's true, and in some cases that might be a perfectly reasonable thing to do. But a big problem with that, a big drawback to using linear regression in this kind of situation is that it can give predictions that are outside of 0 and 1. So if the outcome is binary and our prediction is 7, that's certainly a little bit strange. Or if the outcome is binary and our prediction is -5, it's not really clear what to do with that. So if we want to have a model that can only make predictions that are between 0 and 1, we can do it. There are a number of different ways to do it, but one of the most common is called logistic regression. Now, I should just say that this lecture assumes you have some level of familiarity with logistic regression from, say, an introductory econometrics course. If that's not the case, or if you're just a bit rusty, then you can click on this link here to see some lecture videos and notes from my materials for teaching logistic regression to the first-year master's students at Oxford some years back. So, what is logistic regression? Just a quick review. Also known as a logit, it is a model for the probability that some outcome y is equal to 1 given some predictors x. And in particular, the model is that that probability equals g of x prime beta, where g is the cumulative distribution function of a standard logistic random variable. If you're not familiar with that random variable, again, you can look at my lecture videos. You can also click on this link on the slide to view the Wikipedia page for that distribution. So again, I'm going to assume you already have some idea of the mechanics of this model. So today's lecture is going to focus instead on intuition and implementation using R, which I have found, at least in the past years, are things that students often struggle with. So the first thing we have to understand about logistic regression is there are 2 equivalent ways to represent it. Neither is right or wrong, they're just 2 different ways of looking at the same thing. The first is the one that I've already shown you. In this case, we imagine a model for the probability that y equals 1 given x, and we express that as a nonlinear function of data, which is x, and parameters beta. So using the command in R for the CDF of a standard logistic random variable, our model is that the probability that y is 1 given x is equal to p logis of x prime beta, because p logis is p stands for probability, so this is the CDF of the random variable whose code is logis, short for logistic. That's one perfectly reasonable way to express this model, but another equivalent way to write the model is as follows. It is that the log of the odds that y equals 1 given x are a linear function of data and parameters. In other words, if we remember what odds are, the odds are the probability that the event occurs divided by the probability that it doesn't. So here, we're talking about the logarithm of the odds that y is 1. So the odds that y is 1 are the probability that y is 1 divided by the probability that y is 0. And again, everything here is conditioning on x. So another way of expressing logistic regression is to say that the log of the ratio of the probability that y is 1 given x to the probability that it's 0 given x are equal to x prime beta. Now, if you're anything like me, the first time you saw these log odds, you thought, well, this is really quite complicated. Why don't we just work with the simpler probability that y is 1 given x? Because after all, the probability that y is 1 given x is just the same thing as the conditional expectation of y in this case. Since y is binary, so its conditional expectation is just the same thing as the probability that it's 1. And that's true, but I'd really like you to give odds a chance. So in some ways, this lecture is actually an advertisement for odds, because it turns out that odds just give a very natural and very convenient way of thinking about lots of problems in probability, not just logistic regression. So let's step back and let's think about odds in the abstract. We're going to take a little bit of a detour. We're going to hold off on saying anything more about logistic regression for a bit. And I'd like to make a strong claim. My claim is that you may think that probabilities are more intuitive than odds, but you're wrong. Like me, you were simply brainwashed by your early education to think that. So let's see if we can change our preconceptions today. What are the odds of an event A? Well, as I mentioned before, they are just the probability that A happens divided by the probability that it doesn't. And I use the convention of a superscript C to refer to the complement of an event. So P of A is the probability of the event A, and P of A C means the probability of A complement, so the probability of not A. Some other people like to write that as A bar, or they use various other symbols, but I use a superscript C. So the complement rule tells us that the probability of an event not occurring is 1 minus the probability of it occurring. So the odds are just the probability of A divided by 1 minus the probability of A. Okay, so let's remember the Monty Hall problem, everyone's favorite example. You're going to pick a door at random. Behind the doors, we have a car, and then a goat, and behind another door, there's a goat. Okay, so if you just chose a door at random, what is the chance you're going to get a car? Well, that is 1/3. Why? Well, the probability is the number of successful cases divided by the total number of cases in this case, because they're all equally likely. So it's the number of cars divided by the total number of items, 1 divided by 3. What about the odds? Well, the odds of getting a car, I should have said a moment ago that we were calculating the probability of winning the car if you just choose a door at random. So now let's calculate the odds of winning the car if you just choose a door at random. Well, those are the number of cars divided by the number of goats. So you could think about odds as the probability of A divided by the probability of not A, but it might be simpler to just give yourself a simple example like drawing from an urn or doing a simple probability experiment that has some number of successful outcomes and some number of unsuccessful ones. In that case, the odds are just how many good things are there divided by how many bad things, how many successful outcomes divided by how many unsuccessful outcomes. So in this case, 1/2. And the point I'm trying to make here is that there's really nothing special about counting the number of cars divided by the number of items. In fact, in some sense, you could argue that's a little bit more unnatural of a description of that list of items, car, goat, goat, than just counting up how many cars are there relative to goats. So viewed from that perspective, actually, maybe the odds are a bit more natural. Okay, now to really see why odds can be useful, and for me to kind of convince you that it's worth spending the time to reorient the way you think about these things, I'd like you to consider the following example. Now, usually in my videos, these exercises are things that you will complete separately from the lecture, and there are solutions on the course website. But in this lecture, there are a few exercises that I want you to pause and complete because I will talk about them a bit later in the lecture. So to kind of get the most out of this experience, you really, really need to pause the lecture and kind of not look ahead, because I want you to think about how to solve this problem using what you already know, and then I'm going to show you how odds can make it much easier. So please pause the video now, and we'll return in just a moment. Okay, so this is a very standard Bayes rule question. It's one that I even use with my first year undergrads, but it's kind of a pain. It's, at least for me, I don't find it really easy to do this in my head. So how could we compute the probability that Alice has breast cancer given that she tests positive? Well, we need some notation. So let's define T to be the event that she tests positive, and let's define B to be the event that she has breast cancer. So we're trying to compute the posterior probability. That's the probability of B given T. In other words, the posterior is the probability of some hypothesis, some claim, given the evidence. So here, the evidence is the test result, and the claim, or the hypothesis, is that Alice has breast cancer. Okay, so we know Bayes' theorem, probability of B given T is the probability of T given B times the probability of B divided by the probability of T. And here, the probability of B is the base rate. That's the underlying probability of breast cancer in the population of people from whom we took Alice as an example. And we know how to convert the denominator, probability of T, which is sometimes called the marginal likelihood. We know how to convert that into a more complicated object that we can compute using the numbers we were given in the problem statement by using the law of total probability. So the probability of T is, in this case, the probability of T given B times the probability of B plus the probability of T given B complement times the probability of B complement. And you can plug in all the numbers and you get a result of around 0.32, which many people find counterintuitive the first time they encounter it, because they say, look, this test is very accurate. Why would someone who tests positive be less than 50% likely to have the disease? And the answer is, well, the test is accurate, but the disease is actually really rare. So the base rate is quite small, and Bayes' theorem shows us how to do that. Okay, fine, but this posterior probability is actually a highly nonlinear function of all the numbers in the problem statement. So, and just by the way, in case you're interested, these numbers have some names. You can look up the names sensitivity and specificity, which are often used in medical diagnosis contexts. So this is hard to do in your head, and it's very hard to see how the answer is going to change if these numbers change. And the reason is that probability is just a clumsy way of representing the information. So rather than this usual approach, let me encourage you to think about this in terms of odds. Odds make things easy. The reason they make them easy is because the part of the previous slide that made our lives miserable was that denominator, where we had the probability of T and then we expanded it using the law of total probability. But when we're working with odds, that denominator will actually cancel. So why is this? Well, the odds that Alice has breast cancer, given that she tests positive, remember, odds are the probability of an event occurring divided by not occurring, will be equal to the probability of B given T. So that's the probability that she has breast cancer given that she tests positive, divided by the probability of B complement given T. That's the probability that she doesn't have breast cancer given that she tests positive. So we can apply Bayes' rule twice. First, we do it for the numerator, which comes directly from the previous slide. And then we do it from the denominator, which is identical, except for the fact that we now have a B complement where we used to have a B. But the key thing to notice is that once we write this ratio of two big fractions, we see that the denominators of each of the fractions are the same, and so they cancel. So when we write things like this, we see that these posterior odds, that's what we call the thing on the left-hand side, the probability of B given T divided by B complement given T. These posterior odds are equal to a product of two things. The first thing is the ratio of the probability of B, unconditional, sort of no conditioning on T, to the probability of B complement. So that thing is called the prior odds. So those are the odds before we have observed this test result. Remember, Alice tested positive. So this says the posterior odds, the odds after seeing the test result, are equal to the prior odds, the odds before seeing the test result, multiplied by something. Now, what is that something? Well, that something is the probability of testing positive given that you have breast cancer, divided by the probability of testing positive given that you don't have breast cancer. Probability of T given B divided by probability of T given B complement. That thing also has a name, and it's called the likelihood ratio. So the likelihood ratio tells us how the data we've observed, how the results of the test, how the evidence bear on our hypothesis. So the likelihood ratio is the place where the data can inform the posterior. The prior odds is the place where the base rate can inform the posterior. And very conveniently, the posterior odds are just a product of these two things. And that just turns out to be so much easier to work with than that unwieldy expression that we had on the previous slide when we forced ourselves to think in terms of probability. So now let me show you. Okay, let's make it easy. Prior odds of 1 over 99. So what would that mean? That would mean that there is one woman with breast cancer for every 99 without. Okay, so that would be the prior odds in this example. What is the likelihood ratio? Well, the likelihood ratio is 95 divided by 2. How come? Well, of 100 people with women with breast cancer, 95 are going to test positive. That was stipulated in the problem statement. And of 100 women without breast cancer, 2 are going to test positive. That was also in the problem statement. So the likelihood ratio is 95 over 2. So all we've got to do is multiply these two things together. And if we just look at those numbers, it's pretty clear. Now, the 95 and the 99 do not exactly cancel, right? But they come close. So if you're just sort of doing this in your head and you're getting a rough approximation, the odds here are about 50 over 100, or about 1 over 2. So what are odds of 1 over 2? We could try to convert back and forth between odds and probabilities, but I want you to start thinking in terms of odds directly. That's why I showed you that silly Monty Hall example from before. So remember the car and the goats. 1 over 2 are exactly the same odds as the odds of drawing a car when you take one draw at random from car, goat, goat. Okay, so now if you really want to know what the probability is, you can see immediately that it must be 1/3. So notice that in our head, with no complicated mathematics, well, we have to know the theorem from the previous slide, but nothing too difficult, we can immediately see what the odds are going to be, 1 to 2, which we know means a probability of about 1 in 3. So that was easy. That I can do in my head, and I can also see how the answer is going to change if the base rate changed. That would change the prior odds, or if the characteristics of the test changed. That would change the likelihood ratio. So here is the mantra I'd like you to recite 100 times before bed every night. Odds are on a multiplicative scale. What do I mean? Well, I've said it before and I'll say it again. The posterior odds are a product of two things. The prior odds multiplied by the likelihood ratio. So what? So that means scaling the prior odds or the likelihood ratio scales the posterior odds by the same thing. So let's modify the problem. Let's suppose that instead of one woman with breast cancer for every 99 without, let's say that there's 1 for every 999 without. So this would be making breast cancer much rarer. So then the prior odds become 1 over 999. So to get the answer, all we would have to do is divide our previous result by 10. So the odds would be 1 in 20. Now, what are those odds like? They're like drawing from 1 car and 20 goats. That's how to think about it. Don't convert to probability. Just think about it like cars and goats. Okay, here's another example. Suppose the sensitivity of the test increases to 99%. So that would be the probability that you test positive if you have breast cancer. And suppose the specificity falls to 95%. So the specificity is the probability of testing negative if you do not have the disease. If those terms are new to you, you can go back a few slides and there are links to Wikipedia where they are discussed in detail. So what would happen in this case? Well, the likelihood ratio would then become 99 over 5. So that's about 20. And what would happen then? Well, the odds would be 20 over 100, which are a fifth. So that's like 1 car and 5 goats. Just notice how easy that is to get the new answer as you change all the numbers. You can just do all of these in your head, which was not the case when we tried to work with probabilities. So because the odds are on a multiplicative scale, it follows that the log of the odds will be on an additive scale. This is actually pretty easy to think about as well. So the reason I want to bring up log odds is not just to add more complexity. For the problem that I've just described, you can work with odds, that's fine. But log odds are very helpful for thinking about logistic regression, which is the whole point of this lecture to begin with. So when we take the logarithm of the expression from a couple slides back, we obtain the following expression. The log of the posterior odds is equal to the log of the prior odds plus the log likelihood ratio. Maybe you've heard of the log likelihood ratio. That's a thing. It occurs in statistics and econometrics all the time. So this is actually really easy, because if multiplication was easier than that mess of the original Bayes theorem and the probability scale, addition is about as easy as you can get. So you could use this to do really simple back-of-the-envelope calculations. So computers, like to use logs base 2. Mathematicians like to use log base e. But for human beings, it's easier to use log base 10. So let's think of some prior odds of various diseases. So maybe a common disease, like a cold or flu, has prior odds of 1 to 10. So that would mean it's like drawing from 1 car and 10 goats. Of course, you don't want to get sick, but you do want to get the car, but you understand my point. A rare disease, we could maybe say, has prior odds of about 1 in 100. Maybe a very rare disease has prior odds of 1 in 1,000. So these would be a way of expressing the base rate as odds. Okay, so what are these on the log base 10 scale? Well, they're -1, -2, and -3. What about likelihood ratios for various diagnostic tests? Well, you could plug in your favorite sensitivities and specificities, and I've plugged in a few here. So for a test that's kind of okay at discriminating between whether you have the disease or not, that test might have a diagnostic value that gives a likelihood ratio of 10. A good test, one that's better and does a pretty good job, that might give you about 100, and an excellent test might give you about 1,000. So again, these are 1, 2, 3 on the log 10 scale. So simply by adding these numbers, you could very quickly get a sense for how likely it is that someone has the disease based on how common that disease is and how good the test is. And now it's time for you to work on an exercise. So again, in some of the exercises today, I'm going to be talking about them in the lecture. In others, I won't. So it's really, really important to pause and ponder these. So the first 2 of these are about understanding the units of odds and how these units kind of relate to 2 things being equally likely or not. Then the third expression is an R programming exercise, which asks you to do a bit of algebra and then asks you to check your algebra using R by making a simple plot. So please pause the video and think through these exercises now. All right, so let's talk about the first couple of these. Probabilities versus odds versus log odds. Probabilities are highly nonlinear. They are bounded below by 0 and above by 1. And as you well know, a probability of a half means that an event is just as likely to occur as it is to not occur. What about odds? Well, we've said it before, odds are multiplicative. What are their bounds? Well, if you think about it very carefully, you think about cars and goats, If there are some objects in the set, then we can't really calculate the odds if there are no objects in the set from which we're going to draw. So if you think about it, the odds have to be bounded below by by 0. So what would that be like? That would be like if there is no car and there's just a ton of goats. Then the odds of getting a car would be 0, because there are 0 cars divided by some number of goats. But the odds can also become large. They can become actually as large as you want. They are unbounded above. So to think about this, imagine that we had an experiment with lots and lots and lots and lots of cars, right? And only one goat. What would the odds be there? Well, it would be the number of cars. So if we had 1,000,000 cars and one goat, well, the odds could be 1,000,000. If we had 1,000,000,000 cars and one goat, the odds would be 1,000,000,000. So the odds are actually bounded below by 0, but unbounded above. And if we think about our original example with 1 car and 2 goats, well, that gave us odds of 1 to 2. How would we get odds of 1 to 1? So odds of just 1. That would be if there were just as many cars as goats. So in that case, the two outcomes, car and goat, are equally likely. So whereas with probabilities, a half means equally likely, with odds, 1 means equally likely. And to figure out what's going on with log odds, we can just take our intuition for logs, and then we can take our intuition for odds and then take the logs. So we know that log odds are additive. They are unbounded above and below. The reason for that is that the logarithm is tending to minus infinity as the argument of the function tends to 0. And we know that the odds can get as close as you want to 0. But the logarithm is an increasing function. So because the odds are unbounded above, so is the log odds. What's nice about log odds is that 0 means that A and A complement are equally likely. How do we know that? Well, that's because the log of 1 is 0. And on the odds scale, 1 means that A and its complement are equally likely. Now, we are finally ready to get back to thinking about logistic regression after a lengthy diversion to talk about odds, but I promise it was worth it. So, how does changing x change the probability that y equals 1 given that x equals that particular value? Well, that's a little bit irritating. We can do it. So we've got to compute the derivative of p logis with respect to x. Okay, what have we got here? P logis of alpha plus beta x. So I've decided to make my regression model as simple as possible. There's only going to be one regressor. How do we compute that? Well, we're going to use the chain rule. And when we do that, we have to pull a beta out front. And the derivative of p logis, which is the CDF of a standard logistic distribution, is d logis, which is the density of that distribution. So that's just the fundamental theorem of calculus. Okay, so what can we say about this? Well, d logis is a density. So wherever we evaluate that density, it's positive. Anywhere on its support, it's positive, and its support is the entire real line. So that tells us that this derivative is always going to have the same sign as beta, because the derivative equals beta times something that is positive. But the magnitude of the derivative does not just depend on beta. Of course, it does depend on beta, but it also depends on alpha, and it also depends on the particular value where we evaluate x. So, as I said a moment ago, probability is a highly nonlinear function, and that carries over immediately to logistic regression. So, expressed on the scale of probabilities, logistic regression partial effects are highly, 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 highly nonlinear. And we can sort of think about this by remembering what a CDF looks like. So p logis is a function that eventually flattens out. It eventually becomes 1 if its argument gets big enough. And when that function has flattened out, the derivative is going to become very, 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 very small. Again, everything is easier with odds. So the thing about logistic regression that's so convenient is that it has a natural representation in terms of odds, and the p logis function itself takes a really nice, simple form. So let's recall from earlier in this lecture that the following two expressions are equivalent. First, the probability that y is 1 given x is equal to p logis of alpha plus beta x. Second, that the log odds that y is 1 given x are equal to alpha plus beta x. And again, I'm making life simple. There's no reason to bother with lots of regressors here. One will suffice to get the point across. I'm sure that if you'd like to add others, you can do that at home. So what follows from this? Well, we've got the log odds equals alpha plus beta x. So raising each side, taking e to each side, I should say, we end up with the odds that y equals 1 given x equals e to the alpha plus beta x. So exponentiating both sides is what I meant to say. Sometimes it's very hard to find the words for some reason. Okay, so what does that tell us? That means if you increase x by 1 unit, what happens to the log odds? Well, that adds beta to the log odds because log odds are linear. That's what's so nice about this logistic regression model. What happens to the odds? Well, increasing x by 1 unit, the odds are e to the alpha plus beta x. So we went from e to the alpha plus beta x to e to the alpha plus beta x plus 1. So now inside of the exp, we've got this extra beta hanging around. And so what does that mean? Well, that's the same thing as multiplying the right-hand side by e to the beta. So on the odds scale, increasing x by 1 unit multiplies the odds by e to the beta. All right, and now it is time for a slightly more complicated exercise. I would draw your attention in particular to exercise number 2, which talks about the divide by 4 rule. This is a very helpful rule in practice. It says that if you take a coefficient from logistic regression and you divide it by 4, that actually gives you the maximum possible effect of changing the associated regressor by 1 unit on the predicted probability that y is 1. So in this exercise, I'm going to ask you to figure out where that comes from, because if you can work it out from scratch, then you'll always remember it. All right, so now we're finally ready to simulate some data from a logistic regression model. And there are several different ways to do this. I'm going to show you 2 conceptually distinct ways of achieving exactly the same outcome. It's useful to think about them for a couple of reasons. One is because you do sometimes see these different ways in econometrics books. Another is because it really helps you to get a deeper understanding of random utility models, which are a topic that you may encounter if you do some structural work in econometrics, because the logistic distribution can be very convenient for building up some simple and even more complex random utility models. But one of these approaches is much more kind of consistent with the framework of those models. So let's start with the direct approach. Here, we're going to first simulate some regressors, x, choose some parameters, beta. Then we are going to calculate the probability for each observation, the probability that y is 1. How do we do that? Well, we just plug x prime beta. So for that particular observation, observation I, we have xi prime beta. We plug that into the logistic CDF to get a probability. That function always spits out a number between 0 and 1. X prime beta may not be between 0 and 1, but the output of p logis is always between 0 and 1. This is one of the features that we were looking for when we first decided to use logistic regression instead of linear regression. We wanted it to make predictions that are bounded between 0 and 1, and it will. So once we have all those probabilities, then we can simply make independent Bernoulli draws with those specified probabilities. So let me just make it really simple. Maybe I have 2 observations, and for the first observation, my x prime beta, when I stick it into p logis, that gives me 0.2. Okay, well then for that particular observation, I simulate y as a Bernoulli draw with probability of success 0.2. Now suppose for my second observation, x2 prime beta, when I stick that into plogis, I actually get 0.6. Well, that means that to simulate the y for that second observation, I'm going to make a Bernoulli draw with probability of success 0.6. So that is the direct approach. There is also an indirect approach, which is typically referred to as the latent variable approach. Now, the first step is exactly the same as before. We simulate some regressors x, and we choose some parameters beta. But the other steps are new. So the reason this is called a latent variable approach is because it involves us drawing some unobserved random variable epsilon, whose only role is to help us create y. It's not a thing that we could ever observe in real life. We could kind of postulate that it exists in some kind of abstract sense, but it's not something we could ever see or directly measure. So it's latent, in other words, it's hidden. So we make draws of this latent random variable epsilon, and we draw these guys as independent and identically distributed standard logistic draws. You may think about these as kind of random utility shocks, so differences in individuals' preferences. That would give a connection to random utility models, if you like. Then we simulate yi star, which is also a latent variable. We can't see it, so that's why I put a star on it, as xi prime beta plus epsilon I. So in this simulation, steps 1, 2, 3 look exactly like how we would simulate from a standard linear regression model. So where does the logistic thing come in? Well, okay, the first place it comes in is the epsilon is being drawn from a logistic distribution and not from a normal. But, in some sense, that's not really a big deal. If you plot the logistic density, you take a look at it, it's not that different from a normal distribution. Of course, it's not the same, but it has a kind of similar shape, and there's a family resemblance. So the thing that's going to be new actually comes in step 4. So in order to get the observed outcome y from this latent y star, what do? Well, we've got to use some kind of a cutoff to determine when y is going to be 1 and when it's going to be 0. So we set y equal to 1 if y star is positive, and we set it equal to 0 if y star is negative or 0. Of course, it's not important what we do when y star is exactly 0, because that has probability 0. That will literally not happen because the logistic distribution is continuous. And I claim that, in fact, these two approaches amount to the same thing. If you simulate your x's in the same way, and if you choose the same parameters, then either of these approaches will give you exactly the same conditional distribution of y given x. One of them does not have recourse to this latent y star. The other one does, but other than that, they're identical. Here is an example of the latent variable approach. So the first thing that I'm going to do is I'm going to set the seed so that this is replicable. Then I'm going to choose a number of observations for my regression. So I decided to have 500. And I could draw my regressor x any way that I like. I just decided to make draws from a normal distribution. And I gave that normal distribution a mean of 1.5 and a standard deviation of 2. It's always important to remember that when we use the rnorm command to generate random draws, that we're specifying the standard deviation, not the variance. So you can see that in line 4 of the code block. The next thing I'm going to do is I'm going to generate y star. Now in my code here, I don't actually have a line that defines epsilon, but my epsilon appears in line 5 nonetheless, because I have y star gets 0.5, that's the intercept, alpha, plus 1 times x, so my beta here is 1, plus r logis n. And what r logis n does is it makes n IID draws from a standard logistic random variable. If we don't specify any parameters to that function besides n, r is going to default to a standard logistic. So what this does is it generates the latent variable y star, which is kind of like the underlying ordinary, linear regression with continuous outcomes. That's line 5. Finally, in line 6, we are going to convert the y stars, which we can't observe, the latent variables, into the y's, which we can observe. And the way that we do that is we make y 1 whenever y star is positive, and we make it 0 otherwise. Now here in line 6, I'm using a convenient trick that exploits coercion. So think all the way back to our first lecture on base R. We talked about coercion there. So if you look at line 6, you'll see I've written y gets 1 times, parentheses, y star greater than 0. So let's look at this right to left. Y star greater than 0 takes the vector y star, which I generated in line 5, and y star is a bunch of random numbers. It then compares those random numbers to 0, so it does that using recycling. So 0 is a scalar. Well, R doesn't have scalars, it's a vector of length 1, but 0 is of length 1, y star is of length 500, so we're comparing each of those y stars to 0, and we're going to get a true whenever the y star is bigger than 0, and a false otherwise. So the parentheses in line 6 give us a vector of length 500 containing logical values. Now I don't want logical values, I want numbers. I want 1s and 0s. So how do I convert the trues to 1 and the falses to 0? There are many ways to do it, but one of the simplest is to use coercion. So I am going to multiply everything by 1. And we know that the rules of precedence for coercion say that a numeric is going to beat out a logical. And when logicals are coerced, true becomes 1. So this is a handy trick that you may find useful in different contexts. Certainly I find it useful here. And when we're all done, we can construct a nice tidy tibble with 2 columns, x and y, and I'll just display it for you there. So we have our x values and our y values, and that's all that we're going to need. I've shown you how to use the latent variable approach. So now I would like you to write code that accomplishes the same thing, but instead uses the direct approach. This, remember, will require you to compute some probabilities. Namely, for every observation, you'll need to compute the probability that that observation will have its y value equal to 1 by using its x value. All right, now we're approaching the grand finale. We're actually going to be able to run some logistic regressions. So there is a base R formula for logistic regression, but it's actually more powerful than that. It is used to estimate a whole host of models from a big old family of models called the generalized linear models. And if you click on this link, you can see a Wikipedia page that talks about generalized linear models. I'm not going to get too much into the weeds about what generalized linear models are here today, so let me just talk about some specific examples. GLM works very similarly to how LM works. Remember that LM is the command for linear regression in R. So it takes 3 arguments in this case. 2 of those arguments, formula and data, should look familiar. So formula is just like we had in LM. So all the formula syntax that you know and love can be used here with tildes, pluses, and so on. Data also works just like with LM. So the thing that's new is this family argument. What family is doing is it's describing what are called the error distribution and the link function. If you don't know what those are, don't worry about it too much. I'm just going to give you 3 examples. So to run logistic regression, which is our goal today, you would specify family equals binomial, link equals logit. If you wanted to run probit regression, which you may know is very similar to logistic regression, except when you look at the latent variable version of the model, rather than a standard logistic, it has a standard normal, you can do that too. Here you specify family equals binomial, parentheses link equals probit. And if you want to run Poisson regression, that is another instance of a generalized linear model. However, it's a model with a different link function and a different kind of outcome distribution. So there you would specify family equals Poisson, link equals log. And what's really nice about GLM, besides the fact that it lets us estimate all kinds of fun models that we enjoy, and that its syntax is similar to LM, is that it's compatible with tidy, glance, and augment. So nearly everything you know about those three functions is going to carry over. If you want to see what changes, then you can read the following help files listed at the bottom of the slide. So you can take a look at the help file for family and the help files for tidy.glm, glance.glm, and augment.glm. So here it is. We are about to run a logistic regression in R. In line 1 of this code block, I have the command to run the regression, and I'm going to store it in an object called lreg. So the command is, first of all, glm. Then I have my formula, which is y tilde x, so I'm running a regression of just y on x. I specify family equals binomial link equals logit, and then I specify the data set, which is my dat. That's the simulation data that I generated before. And if I use the summary command, I can get this long and complicated table of results, but much of it looks familiar. I don't want to get into what null and residual deviance are today, but you can see that I've got my coefficient estimates, I've got my standard errors, and I've even got some p-values here. So it's time for you to now try an exercise. I would like you to, first of all, construct some confidence intervals and then estimate the coefficients. Then I'd like you to play around a bit with these commands like coef, tidy, and glance, and try to see how these work with a GLM model. I'd also like you to try playing around with the model summary command. What do you get? What you'll notice as you go through this course is that I've selected a set of tools for you to learn that all play together nicely so that you can combine them in many interesting and useful ways, which means that every time we learn something new, it allows us to learn other things faster and to do more. So take a few minutes. This might be a bit of a longer one. You can always check your answers against the solutions on the course website. And after you've done so, you can resume the video. All right. Now suppose we want to make predictions. The command predict works with GLM almost in the same way that it does for LM, but there is a little bit of a quirk. Or perhaps not a quirk, there's just a bit of a twist. So if what you want are the predicted probabilities, which probably are what you want, then you need to set the argument type equals response. So here's an example. If you want to get an estimate of the probability that y equals 1, given that x is 0, we can use predict lreg. So lreg is the regression object that we created with GLM. And then as before, as we did when we combined predict with LM, we specify the new data argument. So there we've got to feed it a data frame, and I've given it a very simple one, data frame x equals 0. So I'm just setting x equal to 0. Then I specify type equals response, and I get a predicted probability of about 0.6, which makes sense in this context. Okay, so now we could try something else. We could specify instead the average value of x from the data set, and we would get a predicted probability of about 0.86. You can also get the predictions for all of the observed x values very easily. In this case, you simply don't specify new data, and I'll show you the first few of those. I'm not going to show you all of them because they would run off the screen, so I'm just using the command head to show you the first few. You can indeed use augment with GLM type objects. Here's an example. Here you need to specify type.predict equals response. So if you see when we do that, we get these fitted values. We have in our tibble now the augmented one. We have x, y, then we have dot fitted. And you can see that dot fitted contains these probabilities. So they're all between 0 and 1. And again, it makes sense. If you look at the 6th row of the tibble, you see in that row, x is 2.5, and there the predicted probability is 0.94. That makes sense because in this model, as x gets bigger, the probability that y is 1 goes up. And that's because in the data set, most of the y's are 1 when x is big, and most of them are 0 when x is small. That's how I set up beta in this simulation exercise. Now, you may also want to plot a logistic regression. We made some nice plots of linear regression models in our earlier lecture, but of course, there's something a bit funny about plotting a logistic regression, and that's that the y's can only take on one of two values, 0 or 1. But nevertheless, we can combine the tools we've learned before with the new ones we've learned today. So here I'm going to use ggplot. I'm going to apply it to my DAT. I'm going to specify this aesthetic mapping x, y. So I'm using a bit of shorthand here. The x-axis is going to be the variable x. The y-axis is going to be the variable y. Then I use stat smooth as we did before, but now rather than method equals lm, I'm going to specify method equals glm because we're now using a generalized linear model. And we have to pass some arguments to the method. In other words, we need to tell R what kind of generalized linear model we are actually fitting here. So we need to tell it that it's logit. So I'm going to say method.args equals list, family equals binomial, and that is going to default to logistic regression. So here we can see the plotted probability that y is 1 given x. That's the blue curve. And then we can see the data, which again, they're not that interesting. They just lie along these two bands. We have the zeros, we have the ones, and then we can see their x positions. Now, as I just said, it's a little bit uninspiring, that plot that we've shown before. It can be very hard to actually see how many x observations there are that correspond to a y with 0 and how many with a y of 1. So something that can be very helpful when you're trying to display a logistic regression fit is to add a bit of noise, add a bit of what's called jittering. So what jittering does is it moves points around. It moves them away from their exact location so that they don't cover each other up, and you can see them. So what I'm going to do here is I'm going to add a little tiny bit of jitter in the x and y coordinates. And I can use that using the function geom underscore jitter, or rather the geom called geom underscore jitter. I specify two arguments there. Width is the noise in the x coordinate, so I've set that to 0.5, and height is the noise in the y coordinate. I've set that to 0.1, and you may have to play around with that a bit to get a picture that is visually appealing. But now we can actually see that there's not that many observations for which y is 0. That wasn't really obvious in the previous plot because so many of those black dots were covering each other up that we couldn't really see how many of them there were. So jittering can be a nice way to improve legibility in your plots when you have one coordinate that can only take on a discrete number of values. And now we have reached the end of the lecture, and we have reached the final exercise for you to explore. So here, I'm going to ask you to pull the data set from my website, from an example where I actually carried out the two truths and a lie experiment with my class. So that can be found in the data directory of my website. So you have to go to https://tetrali.com/data/the name of this file, which I've given you on the slide. And here's your opportunity to play around with logistic regression on a real example. So you may want to think about this example. And one of the questions that we might have is, how well did the class do in guessing the correct, which statement is the true statement and which one is the false statement? Were they more likely to be correct when they were certain? How much more likely?